So we have a quiz at the end of class today, the last maybe 10 minutes of class. It'll be quick, just short answer questions, kind of memory type stuff. It's just my way of getting you to read and reread your notes as the semester goes on. And then exam 1.
Is on Monday.
Is on Wednesday, I believe. So what is it today, the 18th? So that would be the 25th. And the topics for exam 1 are going to be everything. Let me check one thing. Did I say anything about this yesterday? Okay, so let's go everything up through vectors. That's the stuff we're going to talk about today. So you have a week to get ready for this stuff with no new material. Yeah, so I'll give you an assignment, a vectors assignment today after we cover all this material. It'll be due Monday, and then on Monday, if you had questions working on this vector stuff, I'd be happy to answer anybody's homework questions on that, but we'll do some example problems today. Anybody have any questions about the exam? We're also in lab this week, we're doing vector-related stuff. Half of you are done already with that. It's a fairly short lab, but it's important for getting kind of an intuitive understanding of what vectors are about.
So you're saying vectors are on the exam?
Yes, vectors are on the exam. So it's like a one-day topic we're going to do, and this is the last topic that's on it. Okay. So we have been talking about 1D kinematics of particles. And in 1D, an object is just moving along a line. Now we're going to get into 2D kinematics of particles. So kinematics still mean the same thing. It means relationships between position, velocity, acceleration, and time. Particles still mean the same thing. It means we're treating objects like they only exist at their center of mass, and that just moves around. But 2D means that things are free to move in a plane instead of along a line. And that changes the way that we have to treat these things mathematically. So 2D means at any location, an object has a full plane of directions to move in. Okay, so remember going back to 1D so I can make the connection between what we've been doing and how it's going to change. In 1D, position, velocity, and acceleration each had two properties. These properties were a magnitude And that was given by the absolute value of these things. And a direction. And the direction was given by the sign. So like, for example, if you had a velocity that was -6 meters per second, what that meant is the magnitude, the speed was 6 meters per second, and the direction, it was moving in the negative direction, okay? In 2D, sign does not work anymore for giving the direction. And the reason is, now there are infinitely many directions that we have to deal with. You know, there's infinitely many directions. And there's only 2 signs. And so that brings up a new mathematical thing that we're going to have to deal with called a vector. This is the object that we're going to use in 2D to represent quantities with a magnitude and a direction. Okay, so the first thing is, think of a vector as having 2 properties, a magnitude and a direction. These are going to be represented by arrows. So if this is a vector, we're going to call this the tail end. And the end with the point is the head. The magnitude is given by the length of the vector, the length of the arrow. And the direction is just the direction that the arrow is pointing. And for us to do math with vectors, so like in the lab, we're going to talk about some sort of intuitive features that vectors have, what it means to add 2 vectors, to multiply a vector by a number, stuff like that. But in class, we're not really going to think of vectors in terms of the arrows as often. Mostly we're going to break them up into what are called components, and we're going to use the components for math. So to do math with vectors, we're going to break them up into what are called components. And here's what the components mean. So if this is the vector, and this is the coordinate system, we're going to get used to always putting the tail of the vector at the origin of the coordinate system to analyze it. And let me give this some length. So let's say this is 1, 2, 3, 4, 5. So in this coordinate system, this is -5. And for y, it's 1, 2, 3. Let's call that 3. Then the components are, you can think of like, if you shined a light from above onto the x-axis, okay, the shadow of this would go down to -5. And if you shined a light on this vector from this side, that light, the shadow would go up to 3. Okay, so you can think of those as like shadows or projections. The projection that goes along the x-axis is called the x-component. And in this case, the x-component is -5. And the projection along the y-axis is called the y-component. And in this case, that's +3.
So this isn't position time graphs anymore?
Correct. This is not, yes, that's a good point. This is not position versus time. Now that we're in 2D, we need 2 axes just to represent a location. We used to just need a number to represent the position. Now we need 2 numbers to represent a position. There are a few different notations for how people represent vector components. One common one is to have, so you would write your vector, let's say this vector is called, I'm going to call it u, okay? And by the way, when something's a vector, to show that it's a vector, you put a little arrow over the top like this. That's just a symbol saying that this thing is a vector. Well, this vector u can be represented as the x component times an I with a little hat over it, and I'm not going to go into where these come from, plus the y component times a j with the little hat over it. And so the thing multiplied by I is the x component, and the thing multiplied by j is the y component. So that's one way you'll see people write this. Okay. Another notation that you'll see is people write the x component first with a comma and then the y component. Like that. They have different notations, but they mean the exact same thing. The one that I'm going to use in this class has the x component on top and the y component underneath and square brackets. So this is the one I'll use. And the top is always the x component. And the bottom is always the y component. Okay, now of all the things I'm going to say today, this one is the most important. This is the one that'll let you figure out components based on stuff you knew before. So this is the most important fact about vector components. And that is if you put the tail of the vector at the origin of the coordinate system, the vector components are the coordinates of the vector's head. Okay, so for example, let me draw a coordinate system. And let's go 1, 2, 3, 1, 2. And draw a vector like this. Okay. The coordinates, the components of this vector, you can get by just figuring out these coordinates. So the coordinates of the head here are +3, -2. So the vector components here are 3, -2. And there are a few things that are useful about thinking this way. So first of all, when you look at a vector, you can always tell by looking at it what the signs of the components should be based on thinking about it like this. It lets you always immediately recognize the signs of the components. Because you can just picture the tail being at the origin, and then the quadrant that the head would be in tells you what the signs are. So let's just go through a few of these to sort of solidify this, make sure you're understanding what I'm talking about. So what are the signs of the components? And I'm going to draw 4 different vectors. So the first one is like that. The second one is like that. The third one is like this. And the fourth one is like this. Okay, so for A, what do you expect the x component sign to be? Yep, so this is going to be negative for x. And what about for y? Positive, yep. So remember, the top one is x, the bottom one is y. For B, what do you expect for x? Negative. Keep the same colors. What about for y? Negative, good. For the third one, what do you expect for x? Positive. For y? Yep. And for the fourth one, what do you expect for x? And negative? No. Yeah, that was good. Okay. So that's the way it works for understanding the signs of the vector components. One other thing you can do immediately is for any vectors that are on the coordinate axes, you can immediately see the vector components. Okay, so for example, let's do two of these. Let's say that, first of all, we have a vector that's like this. And let's say it has a length of 5. And then second, let's say we have a vector like this, and it has a length of, I don't know, 18. Okay, so again, picture the tail of this vector being at the origin, and you're trying to come up with the coordinates that the head would have. What are the components of this vector A? Yep, 0x, 5y, perfect. So this would be 0, 5. Any questions about that? And then what about this one? Well, that squiggly line is supposed to be a straight line. And remember the signs too. So this is going in the negative direction. So this would be negative 18 for x and then 0 for y. Okay? Now, if you are given a vector, and this is going to come up pretty often, as a length and an angle, and so like an example of this would be, let's say we have a vector like this, and we know that the length is 10, and we're given that it makes a 20-degree angle with the vertical. Then first, find the counterclockwise angle from the positive x-axis to the vector. And we're going to call that angle theta. And so in this example, if I draw the coordinate system and I draw the vector over here, we know that this angle is 20 degrees. This is x, this is y. So if you start at the positive x-axis and rotate counterclockwise until you're aligned with the vector, what's the angle that you have to go through? 110. Yep, you have to go like 90 to get here, and then another 20 to get here. And so that theta is equal to 110. And then once you have that, the vector components are the length times the cosine of that angle for the x component, and then the length times the sine of that angle for the y. I think most people in this class have done trigonometry with cosines and sines before. I think there's probably a couple people who haven't, but these are just functions on your calculator. So you really don't have to know anything about cosine and sine to use these. You can just think of it as your calculator is going to, give you something that'll help you find these vector components. One thing is we're always going to do our angles in degrees, so make sure that your calculator is in degrees. And most often, if you use this formula to calculate your vector components, and then you think about the signs of the components and they don't make sense with thinking about it this way in terms of the quadrants, the most likely cause of the problem is that your calculator's in radians and not degrees. Okay, if you have trouble switching your calculator, just come show me your calculator and I can show you how to do it. There's usually like a mode button, but different calculators are different. Okay, so in this case, in our example case, our theta is 110, our length is 10. So for our example, this would be 10 times the cosine of 110, 10 times the sine of 110, and that comes out to be 3.429.40. Anybody have any questions about that? Okay. Let me give you a couple examples to work through. So in our usual coordinate system, CS, I'm going to use that as an abbreviation for coordinate system pretty often. And so just in our usual coordinate system like this, find the components of, so part A, do a vector like this with a magnitude of 5 that makes an angle of 30 degrees with the horizontal. And then for part B, a vector with a magnitude of 20 and makes an angle of 20 degrees. Okay, so see if you can go through that if you have your calculator with you. Okay, so for part A, I'm going to draw the coordinate system and draw the vector with its tail at the origin. And what we want to do is find an angle starting at the positive x-axis that goes counterclockwise and aligns then with the vector. So in this case, that angle is just this. And it's the angle that we're given. It's just 30. So the components of this vector are going to be 5 times the cosine of 30 degrees, 5 times the sine of 30 degrees, if you plug in cosine of 30 degrees into your calculator, you'll get 0.866. And if you plug sine of 30 into your calculator, you'll get 0.5. And so these come out to be 4.33, 2.5. Does it make sense that both of those components are positive? Yeah, it's in the first quadrant, and so think of those as the coordinates. It's a little more involved coming up with the answer to part B. So start out the same way, draw the coordinate system. And then I'll draw the vector with its tail at the origin. And we know that this angle is 20 degrees. Okay? And what we want is the angle that starts at the positive x-axis and goes all the way around to the vector. We want this angle. Okay? Well, notice that this angle 20 plus the angle from here to here, those have to add up to be 90. So, so the angle from here to the vector is 70. Okay? You see that? Any questions about that? And so if we start here and go around, we're going to get 90, 180, plus another 70, and so that angle is 250. And so theta here is equal to 250. And so our answer is 20 times the cosine of 250. 20 times the sine of 250. That's equal to 20 times, if you plug in the cosine of 250, you will get negative 0.342. And if you plug in the sine of 250, you'll get negative 0.940. And so the answers for the components here are negative 6.84, negative 18.80.
Do you care if we put in different angles for our sines and cosines? If you want
No, if you are comfortable doing this stuff, feel free to do what's comfortable. One thing I do want to point out is you can also use the clockwise angle if you call it negative. It's great that that noise isn't annoying. So for this one, it doesn't make too much sense to go clockwise all the way around. It's just making the problem extra complicated, you know. But for this one, you could definitely think like it's easier to just measure the clockwise angle. Then that's just 90 plus another 20 is 110. So you could just call this theta equals negative 110. Plug it into this formula, and you get the exact same answers. Okay. Do the signs of B make sense? We got negative for X and negative for Y. Yeah, it's in the third quadrant, so that makes sense. Okay, I brought up something that's going to be an issue for us. In math classes, they don't worry about stuff like this really, but in physics, there's like a meaning to it. Why did I tell you that the coordinate system is oriented this way? You know, the coordinate system is always oriented that way. Well, in physics, there are times when we're actually going to want our coordinate systems actually relate to something in the real world. And there are times when we're going to want to have the coordinate system rotated to correspond to like the angle of a ramp or something. Okay. So the next thing we have to be able to do is to express the same vector in different coordinate systems. So expressing vectors or vector components in rotated coordinate systems. And the key thing to do when you're doing these is make sure you don't also rotate the vector. The vector just is what it is and it stays there, okay? So the vector doesn't rotate. And still you're going to do the same thing. You're just going to measure theta from the positive x-axis of the rotated coordinate system. Okay, so let me do an example. So let's say this vector makes an angle of 40 degrees with the horizontal, and it has a length of 10. And we want to calculate the components. But we're going to do it in a few different coordinate systems. So the first one we're going to do is just our standard coordinate system. The second one is a coordinate system where the x-axis is down and the y-axis is horizontal. And then the third one is a coordinate system where the x-axis okay, so the x-axis makes an angle of 40 degrees with this horizontal. So the x-axis is that way. That means that this also has to be 40 degrees, by the way. Okay. So the first one is what we've done a few times now. We have a regular coordinate system. Put the tail of our vector at the origin. And we know that this angle is 40 degrees. The angle we want goes all the way from the positive x-axis to the vector. And so what's this angle theta?
220.
Yeah, so you go 90 to get to the y-axis, 180 to get to the negative x-axis, plus 40, so this is 220. Or you could also think that the angle between the negative y-axis and this vector is 50, you know? And so you could go clockwise and call it negative 140. Either one of those is fine. Okay, so now the components. The length of this was 10. So we have 10 times the cosine of 220. 10 times the sine of 220. And so that is negative 7.66, negative 6.43. Do the signs of those components make sense? Yeah, it's in the third quadrant, so those should both be negative. Okay, but now we're going to get to the funky coordinate systems. So the second one, we have the x-axis like that and the y-axis like this. Remember what I said, no matter how the coordinate system is rotated, you don't mess with the vector. So the vector is still just right here, making an angle of 40 degrees with whatever is horizontal there. Okay. But now the angle we want, you have to go from this new positive x-axis. So the angle we want goes all the way from here around to the vector. So what's this angle?
310.
310, yep, 90, 180, 270, plus 40, so 310. Or you could just go the short route. It's 50 degrees clockwise, so you could just call it negative 50 and you'd get the same answer. So this is 10 times the cosine of 310, 10 times the sine of 310. And it'll give you the same answer as 10 times the cosine of negative 50, 10 times the sine of negative 50. And that answer is 6.43, negative 7.66. Okay, do the signs of this one make sense? This is where you got to stretch your brain a little bit. Now remember, yeah, so the quadrant thing still works, but you have to remember to use the quadrants of this coordinate system. So this, where my cursor is the first quadrant, second quadrant, third, fourth.
It's in the first quadrant, basically.
So it's in the fourth quadrant. So it should have a positive x component and a negative y component. Okay? Any questions about that one? Okay, now the last one. So this time we have this coordinate system rotated like this. And it makes an angle of 40 degrees with the horizontal, which means the vector just lies right along the x-axis. Oh, nope, I did it the wrong way. Lies right along the negative x-axis like this. and it has a magnitude of 10. So for this one, you know, anytime you have a vector that's just lying along a coordinate axis, you can just, from observation, tell what it is. This is in the negative x direction with a magnitude of 10. And so this is just going to be 0, negative, nope, negative 10, 0. By the way, you still could use the cosine and sine thing. So to get from the positive x-axis to the vector, that would be 180 degrees. Cosine of 180 is negative 1. Sine of 180 is 0. And so you get that same answer. Anybody have any questions about going from vectors to vector components? That's the end of what I'm going to say about that. You'll get some practice on the homework. And like I said, if any of it doesn't make sense, you know, bring your questions on Monday and I'm happy to answer that stuff. Okay, but now that we know how to go from vectors, the arrows in space, to components, now really we're going to see why it's useful to go to components at all. When you compare the way math works with vectors using components to what you see in lab this week and the complexity of using vectors for math without the components, this is just so much simpler to do. So, okay, now we're going into vector math using components. And the first kind of operation we're going to need to be able to do is to add two vectors. So if you have a vector AB and you're adding it to a vector CD, the sum of those two vectors has an x component that's just a plus c. So you add the two x components, and a y component that's just b plus d. Okay, so let's say that you have a vector 5, negative 5, and you're adding it to a vector 1, 6. Take a minute and calculate the components of the sum of that vector. Okay, so all you do is add the two x components, so you get 6 here. Add the two y components, so you get 1 here. And that's it. So the sum of these two vectors, you can see from this, the head is, if you put the tail at the origin, the head is in the first quadrant.
And that'd be the final position of it?
Yeah, that would be like, so we're not really talking about positions yet, but if you plot this point, say it's over here somewhere, you know, and make that the head of a vector and put the tail at the origin, it's a vector that looks something like that. The next thing we're going to have to do is multiply two vectors. No, not multiply two vectors. Multiply a vector by a number. So the number I'm going to say is the variable c, and the vector is components a, b. And all you do for these is multiply the number times the x component and then multiply the number times the y component. And you get CA for the x component and CB for the y.
And that'd be like time. too.
Yeah, actually that is gonna be, yep, that's perfectly right. Okay, so if you have -5 times -3, +4, take a second and calculate the vector you get from that. So -5 times -3 is +15. -5 times 4 is -20. And if you want to visualize this, it's going to be +15, -20. So the head will be somewhere like that. And so the vector will be in this direction. And then the last thing that we'll want to do is calculate the length of a vector when you know the components. I'm going to call it the magnitude. So calculate the magnitude of a vector. And the way you write that is as an absolute value. You can think of like the magnitude is the absolute value of a vector. So the magnitude of a vector AB is A squared plus B squared square root. Okay, so calculate the magnitude of the vector 3, -4. Just take a second and do that calculation. Okay, so this is going to be 3 squared plus -4 squared. Take the square root. 3 squared is 9. -4 squared is 16. 9 plus 16 is 25. Square root of 25 is 5. And as far as understanding this, it's the Pythagorean theorem. So if you think of the components, you can think of those as the legs of a vector, or I mean the legs of a right triangle. So this one is 1, 2, 3, 4. Nope. Sorry. 1, 2, 3. And then 1, 2, 3, 4. And the length is the length of the hypotenuse, you know, if this is a vector. This is a right triangle. And so you can see how that just comes out to be the Pythagorean theorem. Okay, and you can combine all this stuff into, you know, a single problem, like say you want to know what 2 times 5, 6 minus 3 times 2, negative 1 is. What are the vector components of this? Well, 2 times 5, 6 would be 10, 12. Negative 3 times 2, negative 1 is negative 6, positive 3. Then add those two together and you get 4, 15. Any questions about how that works? Okay, let's do the quiz.